Hello guys, this is Srinivasra Peruri Math Educator. Yes, look at the board. Linear algebra. It is most important topic in BSc final year, fifth paper, right? So vector space. Okay, right. Actually, what is the definition of vector? A physical quantity which has both magnitude and a specified direction is called vector. I repeat, a physical quantity which has both magnitude and a specified direction is called a vector. Best example is right, displacement, right? Next, velocity, okay, etc. and so on and so forth. Right. Now, scalar means a physical quantity which has only magnitude but not a direction is called a scalar. That is called, for example, mass, temperature, etc. and so on and so forth. Right. Now, how to define vector space? So, like this, let V be a non-empty set. Let V be a non-empty set. That means V contains at least one element. Let V be a non-empty set and plus comma dot are any two binary operations on V. Binary operations means let us take any two elements like this. Let A comma B belongs to B such that yes, A plus B belongs to B. Indirectly closure property. Okay, right. So V is closure under addition. Right. Similarly, dot product means A comma B belongs to B such that AB belongs to B. That's it. So here let B be a non-empty set and plus comma dot B two binary operations on V. Now V is said to be a vector space or B comma plus comma dot is said to be a vector space. This one is algebraic structure. Okay, right. This one is algebraic structure. Algebraic structure means if plus comma dot are binary operations on V, then this set V comma plus comma dot, okay, right, is an algebraic structure. Right. So I repeat, let V be a non-empty set. Let V be a non-empty set and the plus comma dot be any two binary operations on V. Now V comma plus comma dot is said to be vector space if V satisfies, okay, right. First one is V comma plus is an abelian group. V comma plus V is an abelian group with respect to plus. Okay, abelian group means first one is closure property. Closure property. Closure property means for all, yes, A comma B belongs to B such that, yes, A plus B belongs to B. That is closure property. And the second one is actually no need to concentrate closure property. Why? Because plus comma dot or binary operation. Binary operation means nothing but closure property. Right. So with respect to our point of view, student point of view, okay, V comma plus is an abelian group. First one is closure property. Closure property means for all A comma B belongs to V such that A plus B belongs to B. Right. Next one is associative property. Associative property. Yeah. Associative property for all, yes, A comma B comma C belongs to B such that A plus B plus C is equal to A plus B plus C. That's it. A plus B plus C is equal to A plus B plus C. Now third one is identity property. Identity, yes, property. For all, yes, A belongs to B. For all A belongs to B, there exists, okay, 0 bar belongs to B such that A plus 0 is equal to 0 plus A is equal to A. Okay, right. So, for all A belongs to B, there exists 0 bar belongs to B such that A plus 0 is equal to 0 plus A is equal to A. Actually, there exists means at least one. Okay, right. So, I have to impose a condition on this one such that for all A belongs to B, there exists a unique. 0 is unique. Okay, right. For all, yes, A belongs to B, their exit unique zero bar belongs to V such that A plus 0 is equal to 0 plus A is equal to A. This is the correct sentence. Okay, right. Why? Because there exist means at least one. So at least one means more than one also. It is a contradict to this one is it is a contradict to this one beta. Zero bar belongs to V. There exist unique only one. Okay, zero bar belongs to V such that A plus 0 is equal to 0 plus A is equal to A. Now fourth one is inverse property. Inverse property. Yes, for all, yes, A belongs to okay, V, there exit, yes, minus A belongs to V such that A plus minus A is equal to minus A plus A is equal to 0 bar. Okay, right. So, this type property. Of course, in this case also for all, yes, A belongs to V, there exit a unique. Okay, unique. Minus A belongs to V such that A plus minus A is equal to minus A plus A is equal to 0 bar. Okay. Finally, fifth property. Okay, abelian property or commutative property. Commutative, yes, property. Commutative property means for all, yes, A comma B belongs to B such that A plus B is equal to B plus A. Right? A plus B is equal to B plus A. This is okay, first property like this. A set V is said to be a non-empty set. Okay, right. Let V be a non-empty set and plus comma dot or binary operation on V. Okay, in algebraic structure, V comma plus comma dot is said to be vector space if V satisfies okay, abelian property with respect to addition. V comma plus is an abelian group. First one is closure property. For all A comma B belongs to V such that A plus B belongs to V, or U comma V belongs to capital V such that U plus V belongs to, okay, right, capital V. Associative property for all A comma B comma C belongs to V such that A plus B plus C is equal to A plus B plus C, or UVW as our like. Okay, identity property for all A belongs to V, their exit unique. Okay, their exit unique. 0 bar belongs to be such that A plus 0 is equal to 0 plus A is equal to A. Right, next inverse property. For all, A belongs to be, their exit minus A belongs to be such that A plus minus A is equal to minus A plus A is equal to 0 bar. Okay, minus A is called additive identity. Okay, in can be. Yes, commutative property or abelian property. So, for all A comma B belongs to B such that A plus B is equal to B plus A. This one is V comma plus is an abelian group. Is an abelian group. Second property, right? Yeah. C into du is equal to CD into U, where C comma D are scalars. Scalars and U belongs to capital B. Okay, right. This one is first condition. Second one is C plus D into U is equal to Cu plus Du. Similarly, like this. Okay, right. Now, third property. Third property. Now, C into U plus V is equal to Cu plus Cv, where C is a scalar and okay, right, U comma V belongs to capital V. And the fourth property is 1 into U is equal to U, where U belongs to capital V. Yeah, listen beta. Let V be a non-empty set and the plus comma dot are any two binary operations on capital V. Okay, in algebraic structure, V comma plus comma dot is said to be a vector space if V satisfies Roman number 1, V comma plus is an abelian group. V comma plus is an abelian group. Abelian group means 5 properties. First one is closure property. second one is associative property, and third one is identity property, and the fourth one is inverse property, and the fifth one is commutative property. Okay, now case number 2. So C into du is equal to CD into U, where C comma D are scalars and U belongs to capital V. Okay, right. And this one is C plus D into U is equal to Cu plus Du. Okay, where C is a scalar and U belongs to capital V. And C into U plus V is equal to Cu plus Cv, where C is a scalar, U comma V belongs to capital V. And fourth one is 1 into U is equal to U is equal, where U belongs to capital V. This is the definition of a vector space. Now, for example, yeah, example. All right. So this one is R comma plus comma dot is a vector space, no doubt. R comma plus comma dot is a vector. R comma plus is an abelian group, real numbers. R is equal to a set of real numbers. R comma plus is an abelian group, and R satisfies like these properties. Okay, is a vector space. And the second one is Z comma plus comma dot is also a vector space. Z comma plus comma dot. Okay, right? So, and the third one is, right, n comma plus comma dot is not a vector space. Why? Because n comma plus is not an abelian group. Why? Because negative values doesn't belongs to capital N. That's why is not a vector space. Enough. Define vector space. Give some examples. That is the question of vector space now. Yes. Now, subspace of a vector space. Subspace of vector space. Yeah, this one is very important for annual examination purpose, like this. Most important. Define subspace of a vector space. Right? Yeah. Now listen better. Let H be a non-empty subset of a vector space capital V. Let H be a non-empty subset of a vector space capital V. If yes, and H is said to be a subspace of a vector space capital V if first one is 0 bar belongs to V, which implies 0 bar belongs to H. Understood? Right? A 0 element in capital V, which implies 0 element in capital H. Now, second one is H is closed. H is closed under addition plus. That is U comma V belongs to H such that U plus V belongs to H. And the third one is H is closed under scalar multiplication. H is closed under scalar multiplication. That means, now U belongs to H. Yeah. Now C be a scalar. Cu belongs to H, where C be a scalar. Right? So this one is the definition of subspace of a vector space. Listen beta. Let H be a non-empty set. Our simple definition is a non-empty subset H of V is said to be a subspace of a vector space V if H satisfies three conditions. First one is 0 bar belongs to V, which implies 0 bar belongs to H. Second one is U comma V belongs to H such that U plus V belongs to H. And the third one is let a C be a scalar and U belongs to H, Cu belongs to H. Three properties. I repeat. Okay, right? A non-empty subset H of B is said to be subspace if Okay, H satisfies three conditions. One is, 0 bar belongs to V, which implies 0 bar belongs to H. And the second one is U comma V belongs to H, which implies U plus V belongs to H. And the third one is let a C be a scalar and H is closed under scalar multiplication. Okay, right. So let C be a scalar and U belongs to H, CU belongs to H. Okay, right. These three properties enough. Right. Next one is linear combination. Linear combination. Okay, right. Linear combination of S. Yeah. A set S, right, is equal to set of U1, U2 and so on Un. Okay, right. Let S is equal to set of U1, U2, U3 and so on Un be the given set. Now, okay, right. C1 U1 plus C2 U2 plus and so on plus Cn Un, this is equal to S sigma, right, Ci Ui is called linear combinations of the vectors U1, U2, U3 and so on Un, where C1, C2, C3 and so on Cn are scalars. I repeat, yes, let S is equal to set of U1, U2, U3 and so on Un be the given set. S contains only vectors. Now C1 U1 plus C2 U2 and so on so on plus Cn Un is equal to sigma, okay, Ci into Ui, okay, is called all right, linear combinations of the vectors U1, U2, U3 and so on Un. Okay, right. So this is equal to, yes, linear combination of U1, U2 and so on Un, or span of U1, U2 and so on Un. Both are same. Span of the vectors n vector is nothing but linear combination. I repeat. Okay, right. Linear combinations of this set S is nothing but span of S. Okay, right. Span of S. Like this. Span of U1, U2, U3 and so on Un. So span means it is a linear combination of the vectors U1, U2, U3 and so on Un beta, right? Yes. Now linearly independent set of vectors. Yeah, beta. Linearly independent. Right. Now a set S is equal to set of U1, U2 and so on Un is said to be linearly independent if there exist n scalars, C1, C2 and so on Cn, all zeros, such that a C1 U1 plus C2 U2 and so on plus Cn Un is equal to 0 bar. Okay, right. I repeat, a set S is said to be linearly independent set of vectors if there exist n scalars C1, C2, C3 and so on all zeros, such that C1 U1 plus C2 U2 plus and so on plus Cn Un is equal to 0 bar. Okay, right. This is the definition of the linearly independent. So one set given. Now let us take a linear combination is equal to 0 bar or span is equal to 0 bar. Then we have to show all the scalars are equal to 0 or not. If C1 is equal to 0, C2 is equal to 0 and so on, Cn is equal to 0. Okay, right. So C1 is equal to, C2 is equal to, C3 is equal to and so on, Cn is equal to 0. Okay, right. Don't write 0 bar. Why? Because it is a scalar. Right. So now this one C1 is equal to C2 is equal to C3 is equal to and so on, Cn is equal to Cn is equal to 0. So this one is linearly independent. Right. Yes. Now linearly dependent. This one is linearly independent. A set S is equal to set of U1, U2, U3 and so on Un is said to be linearly dependent if they exist n scalars, okay, right, n scalars C1, C2, C3 and so on Cn, at least one of them should be non-zero, at least one of them should be non-zero, at least one scalar should be not equal to 0, that is, okay, right, such that C1 U1 plus C2 U2 and so on plus Cn Un is equal to 0 bar. Okay guys, so what the difference between both? All the scalars are equal to 0 here, but here at least one scalar should be not equal to 0. At least one scalar. Okay, at least one is it is a very dangerous word. At least one means, okay, right, more than one also. Okay, right. Yeah, please give me at least 100 rupees. At least 100 rupees means I'm expecting more than 100 rupees from your side. Okay, that is the difference. That is the meaning of the word at least. It is very dangerous word. So here, okay, a set S is equal to set of U1, U2, U3 and so on Un is said to be linearly dependent if there exist n scalars C1, C2, C3 and so on Cn, at least one of them should be not equal to 0 or non-zero, such that C1 U1 plus C2 U2 plus and so on Cn Un is equal to 0 bar. Okay, right? Yes. Now this, for example, one vector like A bar. A bar is a scalar multiple of another vector B bar. Those are dependent. One vector is a scalar multiple of another vector. One vector is a scalar multiple of another, where C is a scalar. Okay. One vector is a scalar multiple of another vector. Then A comma B are linearly dependent, not independent. Understood? For example, A bar is equal to 2, 4, 6. 2, 4, 6. Now B bar is equal to 1, 2, 3. 1, 2, 3. Now A bar is equal to how much? 2, 4, 6. This one is order triad. That means 2i plus 4j plus 6k. No need to write every time ijk. Order triad means it is a one vector. Okay, right? 3D vector. So the 2i plus 4j plus 6k. Now this can be written taking 2 common here. 1, 2, 3. So that is equal to 2 into B bar. So A bar is equal to 2 into B bar. A bar can be written as, how can a scalar multiple of B bar. So A comma B are dependent vectors. Understood? Right, beta.